This problem is an example of where normal and tangential coordinate systems are very useful. Let's read the problem statement. A race car is initially traveling at 75 miles per hour at point A. As it enters the S curve shown, in order to successfully traverse the curve, the race car driver applies his brakes and decelerates uniformly between points A and B. Point B is located 750 feet down the track from point A. After point B, the race car driver accelerates uniformly for 850 feet until he returns the vehicle's speed to 75 miles per hour at point C. If the total acceleration of the vehicle at point A and point C is 10 feet per second squared, determine the tangential acceleration at point A, the total acceleration and velocity of the car at point B, and the radius of curvature of the track at point C. All right, so this is a lot of information. Let's see what we have. All right, so first we know the velocity or the speed of the car at point A and C. We also know the distance between A and B and the distance between B and C. We know the radius of curvature of point A, that's given in the figure. We know that the total acceleration of point A is 10 feet per second squared and point C. Then it tells us that the car accelerates uniformly, so the tangential acceleration between A and B is constant, and also the tangential acceleration between B and C is constant. And then it wants us to find the tangential acceleration at point A, the total acceleration of point B, the velocity of point B, and the radius of curvature of point C. All right, so let's start solving the problem. All right, let's start with point A. All right, we know that we're going to use tangential and normal coordinates. I mean, the problem said as much, right? It wants us to find the tangential acceleration. It gave us the radius of curvature, so that's pretty key to tell you what coordinate system you should use. All right, so point A. We know the acceleration of point A is 10 feet per second squared, and we write down the normal and tangential acceleration equation. All right, so this 10 is the total acceleration, so that's on the left side. However, this is just a magnitude. So in order to use this vector equation, we need to take the magnitude of it. So that's what we did here. So we took the magnitude. We squared each component, took the square root. All right, then we plugged in the values that we have and came out with a tangential acceleration of minus 3.656. All right, so that's point A. Now let's move on to point B. Point B, we want to find the velocity, right? And we know that the tangential acceleration between A and B is uniform, so that's constant. That means we can use the constant acceleration equations. All right, so we're going to use this one, the v squared one, plug in between points B and A, and we have all those values. So we find out that the velocity at point B is 81.34. All right, now we can go on and find the acceleration of point B. So again, we write down the tangential normal acceleration equation. Now the special thing about point B is that it's an inflection point. That means that the radius of curvature, the center, changes from this side to that side, and it does it at point B. So that means the radius of curvature of point B is infinite. It's a straight line, really, well, a point. So that means this term goes to 0. And the acceleration, or sorry, the velocity will change, right? It goes from accelerating or decelerating to accelerating from A to B to B to C. So that means that we have V B dot is 0. So this term goes to 0. So the total acceleration of B at the inflection point is 0. All right, so let's go on to point C. So again, between point B and C, let's go back and look at the figure. Between point B and C, we have a constant tangential acceleration. So we can use the constant acceleration equations again. So we apply that between points B and C, and we can come up with that tangential acceleration. All right, with that, we can find the radius of curvature. If I can get the page showing. Hold on, there we go. All right, we write down the acceleration equation in the tangential and normal coordinates. Again, we know that the magnitude of the acceleration at C is 10, so we need to take the magnitude of that equation, plug in our numbers, and we can find the radius of curvature.